All right, from now on, in every chapter, I'm going to have at least one section. No, I'm not at least. I'm going to have one section that you're going to do on your own. This is the section here, okay? And it has to do with temperature, range, and spontaneity, all right? And I want to talk about that a little bit first, but you're copying this down now, and this you're responsible for on your own. I'm never going to check these notes. I'm not going to ask you to pass them in, okay? You can do whatever you want with those notes, taking whatever notes you want on that and looking at those examples. But the fact is, you will have on the test a problem like these here or like these here. There's two. They really represent two types of problems you can see on the test, and you're responsible for doing them on your own. However, I am going to give you a little bit of a start on it. Okay, this kind of has to do with something we talked about a little bit yesterday. So I want to start with it. I want to talk about it again. Okay, so we're talking about this equation. All that stuff that you're doing on your own is kind of manipulating this equation, delta G equals delta H minus T delta S. I kind of hinted at it yesterday a little bit. I said, you know, when we find delta, there are four possibilities for delta G, okay? You could have a negative delta H and a positive delta S, negative, negative, positive, negative, positive, positive. And we went over this a little bit yesterday, but I didn't really put it on the board. Okay, because this is something you're going to be doing. It's going to be talking about this in those papers or those pages you're going to be reading. Now, what are the possibilities here? Two of those possibilities will always end up with the same sign. Okay? A negative minus a positive will always give you a negative, right? And a positive minus a negative will always give you what sign? Positive, right? Positive minus a negative. Okay, so these two guys are written in stone. This reaction, if I've got a negative delta H, in other words, it's seeking its lowest energy and getting more random and spread out at the same time, this guy is always spontaneous. Okay, this guy here, never spontaneous. Why? Because both bad things are happening. You have this guy going from low to high energy and becoming more organized, okay, decreasing in entropy. The problem is with these two guys. What happens there? Okay, let me ask you. We said it yesterday briefly. Hello. Yeah. Okay, that's no problem. All right, thanks. Bye. Problem with these two guys. Who could tell me? We'll call this guy A. We'll call this guy B. Which one will be spontaneous at high temperatures? Does everybody agree it's going to be B? Why? Because T is in front of this guy, in front of the entropy. The bigger I make T, the more effect the entropy has. Entropy is saying, yeah, be spontaneous. Enthalpy is saying, no, don't be spontaneous. The more effect I give to entropy, the greater chance he's going to be spontaneous. So this guy will be spontaneous at high temperatures. And this guy will be spontaneous at low temperatures because I don't want T to have a big effect. I want him to be very small because delta S is saying don't be spontaneous. Okay, well, that's what we kind of mentioned yesterday, but I didn't really put it on the thing. Let's talk about what you're also going to have to see in these notes you're going to be reading on your own that has to do with this. Most reactions, you don't realize this. When I have a reaction like A plus B yields C, we're going to have a chapter on equilibrium. Actually, we're going to have 3 chapters on equilibrium. All right? And what we're going to learn is most chemical reactions are like that. They go both ways. Not only does A and B come together to make C, but C, at the same time that this is happening, is breaking up into A and B. And the question is, which one wins out? Which one wins out? When I solve a delta G problem, delta H minus T delta S, I am solving it for the forward direction. So say I think the example problem I did yesterday, I got a delta G that was a positive 173 kilojoules per mole. And we said that reaction, although you didn't write it in notes, I meant to write it, is not spontaneous. You would know that because it's a positive value. Okay? So positive, not spontaneous. You know what I'm talking about? I'm talking about the forward direction. Right? Guess what? If I did all of this stuff for the reverse direction, what would I get? The exact same value, only negative. right? So that's saying, when you say the delta G is positive and this guy's not spontaneous, you're saying the forward direction is not spontaneous. If you were to find it to be negative, you'd be saying the forward direction is spontaneous. The reverse direction will be the exact opposite. So the cutoff point is basically when delta G is 0. At 0, the forward and reverse rates are exactly equal. They're the same, all right, where delta G is equal to 0, okay? If it's, again, if I'm solving the problem, I get a negative value in the forward direction, that's saying it's spontaneous. A positive value saying it's not spontaneous. Okay, if it's 0, I will actually have it at equal. It's called at equilibrium. We're going to learn what equilibrium really is. We're going to calculate equilibrium constant, do all of that stuff. But it comes up, it pops its head up here in a very small way in what you're going to be reading about. If I set delta G equal to 0 in this equation, can I solve for the temperature at which something will be spontaneous? Think about it. Think. Delta H minus T delta S. I can solve for delta. I know what delta H. I look it up in the back of the book. I know delta S. I look it up in the back of the book. I plug in 0 for him because I know that above 0 or below 0 tells me if he's spontaneous or not, right? I turn him into 0, and I solve for T. Say I get T to be 298 Kelvin. That tells me that at that temperature, he is at equilibrium, okay? And then I got to decide, with temperatures above will be spontaneous or at temperatures below will be spontaneous, and that will depend, that's what you're reading about today. That will depend on whether delta S is positive or negative. If I've got a positive delta S and a positive delta H, right? Positive delta S, yeah, positive delta H, that's good. Positive delta S and a positive delta H. 298 is a number I get. If I increase that number, I'm making delta S larger, aren't I? So I'm going to make a better chance of being spontaneous. So this guy will be at spontaneous temperatures above 298, right? But let's switch those around. Say I have negative and negative. Then it will be spontaneous at temperatures below 298. But the point is I'll be solving for T because delta G is equal to 0. If I set delta G equal to 0, remember you're looking all this up on your own, taking your own notes and examples on that. Can you solve that equation for T? Yeah, it's real easy, isn't it? It just becomes T delta S equals delta H, so T would equal delta H over delta S, wouldn't it? So I could solve for the temperature at which it will be spontaneous or not. In other words, where it's at 0. I can solve for the temperature above which it may be spontaneous or below which it is spontaneous. Okay? And it will depend on whether this guy's positive or negative, and this guy's positive or negative. All right, so that's all stuff you got to do on your own. And it's all in this stuff here. Y'all copy that down. This is a tough chapter, I know. There's a lot in it. All right, but I'm giving you rewards about this. Remember, I'm going to have on Monday probably at least a period or 2 of AP practice exams, and I'm going to even let you work together on them, okay? Not totally. Some parts you're going to get to work in groups, small groups. And the more points you get, the more you get right, the more points you're going to get. All right, so it'll help you. Also, I'm collecting homework 3 times this chapter, which again, 10 points apiece is bringing up your grade as well. All those labs were basically 9s or 10s out of 10. So they also helped. We had 4 labs in here. So, except for some people. But most people got 10s out of 10s, I would say. All right, now, good enough. That's the stuff you're doing on your own. You need to look that over. Otherwise, you're not going to know how to do these kind of problems. Okay? All right, let's do the next new thing where I am going to teach you how to do it. And that's the enthalpy. You have to copy the notes here for this. The enthalpy of a reaction using bond energies. You did not get this yesterday, right? I want to make sure I'm not screwing this up again. Because with the schedule I've got this year, it's so hard to keep track of where I am. All right, bond energies. I can actually calculate the enthalpy of a reaction a different way using bond energies. And if you thought using the sheet in the Appendix K, the back of the book, Appendix K, numbers was complicated and there was a lot of mistakes you could make, this has got to be worse, believe it or not. This is definitely worse. In those problems, you had to worry about quite a few things. You had to worry about looking in the right column. You had to worry about looking at the right state. You had to worry about using the coefficients. You had to worry about doing them in the right order, products minus reactants. And you had to worry about doing the math correctly as well. Well, this, believe it or not, actually is at least as confusing, but for a different reason. I purposely saved him for last. All right? And here's the reason why I save them for last. Check out the reaction. Check out the equation for this guy. Why did I not give this guy in the middle? He's the exact opposite, isn't he, of what we were talking about with delta S and delta H, and even delta G can be solved with products minus reactants. Bond energies, you got to do reactants minus products. Oops, I don't want to do that yet. You got to do reactants minus products. Let me first explain why you have to do that. Okay? And then we'll actually do a couple of problems. Okay. Why was the delta H using delta H of formation problems, delta H of formation equations? The delta H of a reaction was the delta H of the products minus the delta H of the reactants. Why was it the exact opposite of this? Here's why. The numbers in this sheet, in the back of your, well, not the back of your books as well, the numbers you're using on this sheet, guess what they are? They're delta H's of formation. It says it right there. Delta H basically with a little superscript 0 and a little f. Delta H of formation. Why does that equation make sense if I'm using delta H's of formation? Because the guys I'm forming are the products, right? So the products keep their same sign, no negative in front of them. The guys I'm breaking up are the reactants. So if I'm using delta H of formation equations in the back, you've always used products minus reactants because you need a negative in front of the reactants to change their sign. I talked about that under Hess's law. Why, in this case, am I going to be using reactants minus products? Because here I'm not talking about the energy given off when something is formed. I'm talking about the energy it takes to break a bond. The energy it takes to break a bond. Who's being broken here? The reactants are being broken, so they keep the same sign. The products are being formed, so every bond you make in the products is going to be the opposite sign of what you look at on this new chart you'll get to use also in a test. All right, this is a chart of bond energies. Okay, so let me pass these out to you while you copy this question down. Okay, copy that guy down. I'm only going to do 2 examples, but they are not short and they are not easy. This first one's not bad. The second one is. Okay. Now, the first one's not bad. You have to worry about the same old you got to worry about every time. Am I doing it the correct order, reactants minus products? But now you get to use a chart. And by the way, I realize some people who had accidentally looked ahead. This chart does not have exactly the same numbers as the chart in your book. Okay? It's okay. It doesn't make any difference. On the test, you're only going to use this chart. All right. Whether those numbers are just changed from better methods of measuring from when I made this chart probably 15 years ago or 20 years ago, and now in this newer book they're a little bit different, or whether I accidentally copied a number wrong, it makes no difference because you're simply using the numbers that are on here, so I'll know if you're right or wrong based on these numbers, not based on the chart in the book. All right. So what would I look up first? I'm going to look up bromine first. All agreed? Because I'm doing reactants minus products. So if I wanted to see the work on the test, here's what I want. I want to see delta H of the reaction equals delta H of the reactants minus delta H of the products. It's the exact opposite of what we saw in the delta H of formation equations. All right? So delta H of the reaction, I'm looking them up. You guys can do that, right? Look up the bromine bond. How much energy does it take to break up the Br2 bond in that chart? What do you think? Everybody see it's 192? You see where I got 192 from? Okay. Do be careful here. What do we have to worry about? By the way, in this one I'll keep my units, and the next one I'm not going to have room. They're in kilojoules per mole as well. Okay. What do I have to worry about in this next one? What do I have to multiply them by? What do you think? Right? I got 3 moles of fluorine bonds to break, so I've got to take a 3 times the F2 bond. The F2 bond being I got 159.
Yeah.
Oh, you already multiplied in your head. Okay, well, I want to put the 159 here just because I want to show it. Okay. Right. All right, so 3 times that number. And now here's the weird one, guys. This is the weird one. I want everybody to tell me what I'm going to multiply this guy by. Yeah, I heard it. I heard it. 6, not 2. What are you talking about? It says 2 right there. Why 6? Because I'm talking about bond energies, not energies that it takes to make an entire BRF3 or break up an entire BRF3. I'm talking about the energy it takes to break up just one BRF bond. If you were to draw out BRF, and by the way, the next one I do it, you're going to want to draw these out. Wouldn't you draw BRF like that, right? You'd have to. You'd have no choice. It has to be drawn like that. How many BRF bonds are being broken? 3. 3 of them in here. 3 times 2 is 6. 6 times BRF's bond, which is 190. Now, this is the number we're a little in question here. In the book, it's a completely different number. We're just going to use whatever's there, which is 197. All right, kilojoules per mole. Is it 197 on there? Again, yeah. It doesn't matter if that's right or wrong. All right, that number may very well be wrong. The number in the book is not even close to that number. It doesn't matter. You're using the one that's on the sheet. I'm not remaking the sheet up just because the numbers, one number's off. All right, get your calculators out. Do the math for that, and let's see what you get. If you all get, because there's again a good chance to make a stupid mistake in that as well. Stupid math mistake.
Why is that question mark?
Again, I think there was something weird about that in the old book for whatever reason. I'm not sure. All right, what did you guys get for that answer? Get it?
I got negative 513.
Anybody else get negative 513? Okay, good. Negative 5. If everybody got it, it's probably right. Kilojoules per mole. So what does that tell you about this equation? It tells you this equation is endo or exothermic? Exothermic. Heat's released or absorbed? Released. Favors spontaneity or not? Favors. Those are the kind of questions you're going to get also on the test. Great. Oh, by the way, one last part before I go on to the hard one. That was the easy one. This is a typical one you might get on the test. It has one guy that's tricky, and the other guys are pretty straightforward. Okay. Here's another one though. Why didn't I multiply this guy by 6? 3 times 2 is 6. 2 times 3 is 6. Why didn't I multiply him by 6? Is that what you're doing? You just multiply by the subscripts? No, it's not what you're doing. That's why I said sometimes it helps to actually draw these out. If I were to draw out the bromine molecule, he would look like that. I mean, if I wanted to draw it completely out, he would look like this, wouldn't he? Right? If I wanted to draw out the fluorine molecule, he would look like this. How many fluorine bonds are there? Just one. How many bromine bonds? Just one. But this guy's got, as I drew a minute ago, 3. So you got to be careful. You don't automatically multiply by the subscript. But you do have to, for example, what about a guy like water? What would I be multiplying by here if I had 4 water molecules? I'd be multiplying by 8. Because the H and O bond, if I were to, again, do the electron dot notation, all right, the Lewis structure, wouldn't he look like that? Right? In which case, I'd be breaking up 1, 2 OH bonds. Got it? All right, good enough. Now, that's why this guy is particularly hard. Check this guy out. There are a number of reasons why this guy is difficult. And would almost surely elicit a mistake on a test. Which is why I'm deliberately not going to give you one like this on my test. Where might you see one this hard? On the AP exam, of course. Where you have to remember and really diagram these out. Now, you are, in one sense, a little bit ahead of the curve. Other people would look at C2H4. I think who haven't had organic, I don't think a lot of people who are taking AP classes across the country right now are doing almost no organic compared to what you guys did. You guys look at C2H4, you see that right for what it is, I would hope, by now. You would draw this, and I want you to draw these all underneath it. you would draw this. Oh my gosh. You would draw this as C2H4. Because we've had organic, right? And that's what C2H4 is. If it was C2H6, it would have been a single bond here, right? And if it was C2H2, it would have been a triple bond. Everybody agree? That's where these bonds come in on the bottom. Double and triple bonds on the bottom. See them down there? That's going to come in. Don't start looking the numbers up yet. Let's diagram the rest of these because it ain't going to be easy. How do I diagram one oxygen we're going to diagram? Again, every one of these has got a trick to it. Oxygen is not going to be diagrammed like this, is he? How did we draw oxygen when we did the Lewis structures for him? He, again, has a double bond in there. And you say, well, geez, we still have to remember how to do Lewis structures? Yeah, you do. All right, I'm not going to go over needed, available, and shared again. All right, but you have to do that in some cases. Like, for example, in carbon dioxide. I'm going to tell you right now a nice little hint. This guy I'm doing on purpose because he contains 4 guys that are very likely to be seen somewhere on the AP exam, where you'd have to know that there's a double bond between oxygen. Do you remember carbon dioxide? Just from the fact that we did them in Chem 1 and in Chem 2, we could do all of this again. We could even do the resonance structures of these guys. We could. But does everybody kind of remember that carbon dioxide looked like this, right? For the same reasons when we were doing the electron dot notations and the Lewis structures, that's what he looked like. It would be nice if you don't have to go back and do these from scratch. There are a few. Water, CO2, O2, and even a simple organic compound like him, where you know the double and the triple bonds. You don't have to go back and do them from scratch. There will be probably a problem on the test, the AP test, where they are going to want you to have formal charges, maybe, and resonance structures. It may ask you a question like that, but that'll be a specific question. It probably wouldn't be in the middle of a problem like this. It'd be nice if I could just do these really quick and go on to the next one, where water is going to look like this. Okay? All right, now once you do that, we can determine the numbers. And it's going to get tough, and you're going to make mistakes. If I let you go on your own right now on this one, I'll guarantee you I would get lucky if half of you get it right. Because the first thing I'm going to do for this guy, remember I'm doing reactants minus products. What bond do I have to look up for the carbon-carbon bond? I got to look at the bottom. I got to look at the bottom where there is a double bonded C. The double bonded C is right there, 611. You see it? So it'd be 600. By the way, the equation again is delta H of the reaction equals delta H of the products, reactants, minus delta H of the products. So it'd be 611, I said? Yeah, 611. So the delta H of the reaction equals 611. For me, I'm going to leave out the units because I won't have room on the board. Okay, and you can too for this example if you want to have room in your paper. But on the test, of course, you should always put them. I won't give you one this hard on the test, obviously. All right, 611 kilojoules per mole. But you say, okay, now I'm going to go on to oxygen. No, you're not. What else do you have? You have to break up 4 CH bonds. 4 of them. 4. So I have to go plus 4 times the CH bond, which is up at the top chart, and tells me is, what, 414? Is that right? You see where that comes from. I'm still on number 1. I'm still on the first guy here. I got to go to oxygen. I got to remember there are 3 oxygens, not just 1. So I have to add 3 plus 3 times oxygen's double bond, not OO single bond, but double bond, which is 498. And now I've got all my reactants done. Now I got to subtract the products. I got to put a big bracket around it. 2 times carbon dioxide, but hold on. How many double bonded COs are there? 2 of them. So 2 times 2 of those is how many am I multiplying by? 4. I mean, who wouldn't have made a mistake in here? Seriously. We just gave you this off the top of your head without going over this. 4 times the C double bonded O, which is 741. Just looking up the wrong number is easy enough. Plus, and there's your water. How many waters? How many? Actually, that's not true. If I say how many waters, there's 2. How many HO bonds are there? 4. 4. There's 2 in each water molecule, and there's 2 of them here. 4 again. This is crazy. HO bond is 464. There it is. Now that is a piece of work. I won't give you one this difficult. It would take us, it'd take you 10 minutes to do this problem on the test anyway. So I don't have time to do it. All right. So you should know how to do these. Get your math out, your calculator out. You can math, and plug them in and see if you can keep everything straight. And these brackets in particular, it can get confusing. You might want to do them separately. And what do you get for your delta H of the reaction? Anybody get an answer? All right. See if anybody got the same. A couple people get the same answer. What did you get, Luke?
Negative
1,059. Okay. If I were going to round for significant figures, looks like all these guys have 3, so I might call 1,060, right, for significant figures. All right. Looks like most of those guys have 3 significant figures. So 1,060 kilojoules per mole. Don't forget your units. Don't forget significant figures. Before I leave this go, let me just say one other thing. I think you'll find that if you were to do this exact same problem using bond energies, and then do this exact same problem using the information from the back of the book for delta H information problems, you would get similar, but not exactly the same answers. You might ask yourself why. It's the kind of like really, really tough question they might ask at the end of one of those free response questions. Why don't these numbers match up? If I get 1,060 here, and if I did it by delta H information way, I might get, I don't know, 1,100. Or I might get a little bit less. I don't know. But the point is, it wouldn't be exactly the same. Here's the reason why. When I look up delta H information equations in the back of the book, I am doing that at the specific temperature it says on that chart for the entire compound. Here, when I do these, I have to assume that I'm taking each one of those bonds and breaking them. Well, in reality, the CH bond that I look up here is not going to have, the CH bond that I look up on that chart is an average CH bond that's on this chart, okay? It will differ depending on whether this C is bound with a double bond or a single bond or a triple bond or something else is over there. I could even have had, remember, I could have a carboxylic acid group over here or something like that. All of that will affect how hard it is to break this bond, okay? And so it's not exactly the same. The general CO double bond and O bond is an average, but there's C double bond O in a carbon dioxide, which is not going to be exactly the same as the C double bond O in an aldehyde, okay? Because they're bound to other things which may change the amount of energy it takes to break that bond, and that's why the numbers are not exactly the same. All right, good enough. Well, I got a couple of problems to give you for homework here. I think they're already over the board there, right? Page 599, 48 to 52, and 57, 58. Work on those now.